Let's move on to Unit 7 problems. What I'm really looking for people to remember is in our number 1 problem, our exponentials, keeping in mind that the faster we grow, it's because we have a bigger growth rate. So if you look here, the 2 is really, if we think about this as y equals a and then 1 plus r to the x, right? If we kind of think of that as our general rule, this 1 plus r must be the 2. So r in this case would be 1 or 100% growth rate. If you notice that to here, the 1.4, 1 plus r must be 1 plus 0.4 or a 40% growth rate. So the top one in part A is growing faster at 100% growth rate versus 40% growth rate. You can also see that same 40% growth rate here. So when I look at that, I'm growing the same in part B and C over here. Which two graphs over here with capital letters look like they're growing the same? And I'm hoping you can see that's in D and E here. So then D and E must be our graphs B and C, but we've got to decide which one's which. So the last thing to keep in mind is the number out front, right? So that A value, if you will, is like your y-intercept. So in that case, this guy right here, this 2, this is your y-intercept. So what does that mean? Here's a y-intercept of 2, and it's part graph for the graph of D there. Then right above that in part B, here's a y-intercept of 1 with the same growth rate of 40%, so this must be graph E. The only other growth graph is C, and it is growing faster, so it would make sense that part A, the top line up here, would be the capital letter C graph. By similar means, when you are decaying, and we know that we're decaying here because the value is less than 1, that's being raised to the power. So this is 1 minus r, and this is 1 minus r. It feels like the one that's growing slower is the smaller number, but that's actually the opposite. This would be 1 minus 0.3, or a 30% decay. This would be, to get to that 0.7, this would be 1 minus 0.5, or a 50% decay. So the bottom one is actually decaying faster, and I think you would say that that aligns with graph B here, is decaying faster, because it's dropping quicker. A is going a little bit slower. Okay, over here, this also involves kind of that inverse notation, right? It doesn't actually look like it, but remember, base 3 exponential and a base 3 logarithm, these are inverses. So we start by getting the ordered pairs for 3 to the x. So I need 2 ordered pairs, 2 or 3 ordered pairs, maybe we'll get 3 here. And then we'll reverse, we'll end up switching the ordered pairs to get the log base 3 graph, and then we'll do transformations. So when I plug in -1 to x in 3 to the x over here, so this would be 3 to the -1 power, which just flips it over the fraction bar, which is just 1/3. So I could graph -1 up 1/3. If I plug in 3 to the 0 power, I just simply get 1. So then over 0 up 1 is an ordered pair on this graph. And when I plug in 1 for x, I get 3 to the first power, which is just 3. So over 1 up 3. So these 3 points in green, in order to get the log base 3 of x, I'm just simply going to reverse the ordered pairs for log base 3 of x. So instead of -1 1/3, I'm going to graph 1/3 -1. Instead of 0 up 1, I'm going to graph 1 0. And instead of 1 3, I'm going to graph 3 1. So you probably recall when we used to tip our head to the side, we could actually see this graph in red is not the actual graph we're trying to graph, but it is close. It's the log base 3 of x. So now we want to look at the actual graph up here. I'll put this one in blue and say, hey, I've got an inside transformation -2, so inside x opposite, I'm going to go to the right 2, and then outside -1, so, and down 1. So I want to take these 3 red points and go right 2, down 1. So right 2, down 1, right 2, down 1. Careful with the 1/3 point here, so right 2, down 1. And then this first graph, maybe I'll just go back to the red here for a second, had a vertical asymptote of 0, so that's also going to shift to the right 2. So now we'll have this vertical asymptote at 2. So this would be our actual graph here in blue. Okay, let's take a look at number 3. This is using properties of logs, or you can swoop in some of these. Right, you get a calculator on the final. Log of 1, if it doesn't show a base, is a base 10. That's our common log. So I'm going to show you why your calculator is going to come up with a different, or with a value here, right? So remember how the swoop works. If we're not sure what this is equal to, let it be equal to some value x. 10 to the x is equal to 1 when we swoop. So anything to the 0 power is equal to 1. Therefore, x would be equal to 0. Right? This is why when you type in log of 1 on your calculator, you get 0. For part B, remember that ln of 7 is up in the exponent position. If you look at your formula sheet, you have a formula on there that looks like b to the log base b of x. So as long as you can get the base of your exponential and the base of your logarithm to line up and be the same, which is really what we have, our b is really an e here, it's equal to just whatever you're taking the log of up there. So in our case, that would just be 7. You could use properties of logs for part C here, right? You have a property that looks like log base b of b to the n is equal to n. That's really what we're saying here. If you were to rewrite this, log base 5, you could rewrite the 125 as 5 cubed. So our b's line up, and that's equal to whatever that exponent value is. So in this case, this would be equal to 3. If you don't like the properties, you can go back to the swoop. Say, let's let it be equal to some value x. Then swoop 5 to the x power is equal to 125. Recognizing that 125 is the same thing as 5 cubed, this can only be true, 5 to the x power equals 5 to the third, if x is equal to 3. In this next one, you could try to swoop this one. So 5 to the x is equal to 0. But you would be stuck here for a very long time, right? There is nothing you can raise that 5 to and end up with 0. And what we saw up here when we graphed that log, I think the red version before we transformed it, we had up here, here, and here, right? The idea is, so here's that general log before it gets transformed for log base 3. I know this is a log base 5, but it would be similar. Right, the idea is that your domain up here is 0 to infinity because there is a vertical asymptote up here. So we can't include 0. So when we take the log of 0, that does not exist because it is not in the domain. Right, so the log of a negative is a problem. The log of 0 is a problem. They don't exist. Okay, let's go back to our problems here. So we'll say this is equal to does not exist or undefined. Continuing on with part E, let's let this be equal to some value x. Remember the base of ln is e. If we swoop this out, we end up with e to the x equals 1 over e to the 9th. So kind of similar to what we saw up here in part C, except for we don't want e in the denominator, this e to the 9th in the denominator. So to switch it over the fraction bar makes it a negative exponent. And now by similar means up here in part C, e to the x equals e to the negative 9. That can only be true if x is equal to negative 9. So this whole thing simplifies it, just negative 9. Part F, carrying on with our swoop here, I think would work really well. So 2 to the x is equal to the square root of 8. 2 to the x is equal to, you could rewrite this as 8 to the 1/2 power. What we're really trying to do is get the bases to be the same. So let's rewrite that 8 as 2 cubed. So 2 to the x is equal to 2 cubed, but still to the 1/2 power. And then recall that a power to a power, we multiply exponents. So this is 2 to the x equals 2 to the 3/2. And again, by similar means as up here, right, we can only have an expression where 2 to the x equals 2 to some other power if their powers are the same. So this whole thing would just be 3/2. Part G is always a little bit tricky, but really this one, and I'm going to switch colors just so that it's very clear where my arrows are coming from. This one is really related to this property that we started with up here in part B, but we're trying to get the 16 and the 2 to be the same base. So in order to do that, I've got to rewrite the 16 as 2 to the 4th, but it's still raised to the log base 2 of 3. So those things are connected by multiplication, right? Power to a power, we multiply. We don't quite have this property up here yet because I've got this extra 4 up there now. So let's take that and put it back up in the exponent position. So that's that power property. So this would be 2 raised to the log base 2 of 3 to the 4th power. Now we actually see this lining up where the 2's are kind of like the b's here. This whole thing then is just equal to what we're taking the log of. So 3 to the 4th or 81 would work. In part H, let's swoop this thing. So let this be equal to x. 8 to the x is equal to 1 over 64. 8 to the x is equal to 1 over 8 squared. Again, I don't want it in the denominator, so let's get a negative exponent and to flip it over. And so x would have to be negative 2 here. Okay, so really using our properties of logs, this would be the first several properties listed on the formula sheet for this. Right, if two things are connected by division inside of a log, then we can expand them out with the same log, so ln and ln here, and we'll connect them by subtraction. So this would be the e to the 5th, and then minus ln of whatever that denominator is, which is the square root of b in our case. So this whole thing over here, you could bring this down, the 5 down front if you'd like. That's one way to see this. So 5 times the ln of e. Remember that the ln of e is equal to 1. So we really just end up with 5 over here. In the second piece, you could rewrite this as b to the 1/2 power, which allows us to bring that 1/2 power down front. So minus 1/2 times the ln of b. I think that's all the further we could go. Recognizing in part B, we're still trying to expand things out, but this time everything is connected by multiplication. So, and there's 1, 2, 3 pieces. So that's going to expand into 1, 2, 3 separate logs, all log base 3, right? All log base 3. This is what we mean to expand. It's currently a single log base 3. We're going to expand it out. There's 3 pieces on the inside of what we're taking the log of. Since they're connected by multiplication inside the single log, when we expand it out, they're going to expand by addition. So 27 would be the first piece, x to the 7th would be the second piece, and the y would be the third piece here. So simplifying this using some of the properties from up above, you could do a little side swoop if you wanted on this first piece. Or you could simply say log base 3 of 27 is the same thing as 3 cubed. Then those bases line up, so it's equal to just whatever that exponent value is. So this whole thing simplifies to just 3. You could confirm that with a swoop if you don't trust me. In the middle, you could bring that exponent down front. So plus 7 times the log base 3 of x. And really with this third piece, there's nothing much to do. Log base 3 of y. There's no exponent to bring down or anything to simplify. So to reverse this process, I'll get a different color, but try to fit this all in on the screen. To reverse this process in part 5, we want to put these things back together. If the very last thing we did over here was brought this 7 down front, then we want to look, that should be the very first thing we do when we're reversing. So it looks like this exponent is already up in the exponent position, but this 4 should go back up in the exponent position. So this is log base 5 of x squared plus log base 5 of 2 to the 4th. This is 2 logs connected by addition, so it's going to be put together into a single log connected by multiplication. So x squared times 2 to the 4th, all inside of the log base 5. You could probably do one more cleanup job on this because 2 to the 4th is 16, so this is the same thing as log base 5 of 16x squared. In this next one, again, if our last move up above was to bring that 7 down front, then when we're reversing the process, that should be the first thing we do, is put any exponents back up in the exponent position. So if there's a coefficient down front. So that's log of m to the 1/3 plus log of n squared minus log of p to the 4th. So again, there's 3 separate logs here. We're going to combine them into a single log. There's no base written, so we can assume this is a log base 10, or the common log. So the log of the things that are connected by addition, those are going to be multiplied. So m to the 1/3 times n squared. The things that are connected by subtraction, that's going to go and be a division piece when we put it into the single log. So the p to the 4th. Probably one last move that could be done here is simply to recognize that m to the 1/3 is the same thing as the cube root of m, still times n squared, all over p to the 4th. Okay, let's move down to 6 through 11. This is kind of a long page here. Let's do 6 and 7 on this page. Remember, there's really 2 cases when we're solving exponentials and logs. There's 2 cases for exponentials, 2 cases for logs. In an exponential, we always want to see if we can get the bases to be the same. So let's start by dividing off the 4 and look at our bases alone. So 27 to the 2 minus x is equal to 3. Recognizing that 27 and 3, we could make those bases the same. So that's going to make our job the easiest, to rewrite the 27 as 3 cubed, but it still is raised to the 2 minus x. A power raised to a power, we're going to have to multiply those exponents. So this would be 3 to the 6 minus 3x equals 3 to the, if there's no exponent, there's a 1 there, recall. So this could only happen, 3 to the 6 minus 3x equals 3 to the 1. That can only happen if those exponents are equal. So what we're actually solving is 6 minus 3x is equal to 1. Subtract your 6 over. So negative 3x is equal to negative 5, or x is equal to positive 5/3 when we divide by negative 3. In this next one, remember there are also 2 cases of your log, right? You can either get a log on both sides or a log on one side. So in order to do that, though, we still have to condense down using the similar properties from what we just did, condense to a single log. So these are connected by subtraction. So the single log is going to be 3x divided by 8 equals the ln of x minus 1. When we have a log on both sides and it's condensed, this could, the ln of this equals the ln of that could only be true if their contents of the log are equal. So we're really just solving the equation 3x over 8 is equal to x minus 1. Let's get rid of the fraction by multiplying by 8 on both sides. That means distributing on the right-hand side. So 3x is equal to 8x minus 8. Subtract your 8x over. Negative 5x is equal to negative 8, or dividing by negative 5, x is equal to 8/5. So we only have exact answers on these ones.